Numerical Computation extra video for Chapter 2. This video should be viewed after you have seen the video on Lagrange polynomial for Chapter 2.2. As we have learned, the Lagrangian polynomial is a very elegant way to write out an interpolation polynomial. However, if you want to actually compute it in a computer, that expression is rather time-consuming and not so fast. So here in this video, we will present a way of rewriting the Lagrangian polynomial aiming at improving computational speed. Let's begin with defining a function L of x to simply be the product of all these terms, that is x minus xi, where the xi's are the node point for your interpolation. And I is the index running from 0 to n. So this expression is the product of n plus 1 terms. And now we define something called the barycentric weights. We call it Wj. There will be n plus 1 such weights for j running from 0 to n. So Wj's in the end, they are just numbers. They are computed as the following. It's a product of xj minus xk, and you go through all the k's except the one where k equals j, because that will make this term 0. So that term you don't take, and then you take all the others. And after you computed the product of it, and you take the reciprocal, the inverse of that number. Okay, so I am a little bit obnoxious that I gave an equation number for this expression, Wj. That's equation number 1, and this will later be used again. So with the definition given for function L and the weights W, we can express the cardinal functions very easily with these two. So the cardinal function Li for the point xi will simply be the Lx, the polynomial with the n plus 1 terms, and divided by an expression that is the weight w at I and over x minus xi. So we see that in this product term there is a term x minus xi, so there would be cancellation for when x is not equal to xi. And the reason for representing it in this specific way will be clear later on after further manipulations. Now, with the definition of the function L and the weights W, now we can rewrite the interpolation polynomial. It's just a sum over the function value Wj here multiplied by the cardinal function Lj and add them all up. And we notice that this L of x appearing in every term that does not depend on the index j. Therefore, we can pull this out outside the summation sign and stay there. This expression here is called the first form of the barycentric interpolation formula. We can now count the total number of computations needed. We see that in order to compute the weights, Wi, we would need of order n square flops of an arithmetic calculation. And then to compute the p-value here, it's just the order of n flops. So just to catch your attention here that this form, the first form of the barycentric interpolation formula, I also obnoxiously give an equation number. I call it number 2. Recall the pros and cons of the Lagrange polynomial. It's very elegant, but then it doesn't offer flexibility when you want to add additional interpolating points. Here, the form 2 surprisingly actually allows such flexibility, as we'll see soon. Let's say we wish to add a new data point. Let's call it xn+1 and yn+1, adding it to the interpolation points. This task now entails 2 calculations. So first, I need to calculate a set of new weights, and by comparing this set and the previous one we have, I see that I just need to divide each weight, wj, by this factor xj minus xn plus 1, the additional point we add. So this computation will cost us of order n+1 flops. And then we compute the new weight n+1 with the expression 1. That was the expression for the weight. And we see that that cost n+1 flops, which from magnitudely speaking is the same order. And thus, adding a new data point would cost us an additional computation of order n+1 flops. So one would say that's rather efficient and not expensive. So taking advantages of the easiness to add additional point and the inexpensiveness of computing it, we have the following idea. That is, this procedure can be applied recursively to define a rather efficient algorithm of computing the weights. Below, we present such a pseudocode. So the code from the first line to the end of the first big for loop here, we actually compute the inverse of the weight. And they are computed recursively as follows. We initialize it by setting the weight for the first point, or rather the inverse of the weight for the first point. And then we go through the remaining points, treating each one as an additional point you add to the interpolating points. And for each point, we carry out exactly the 2 steps that we talked about in the previous page. So first, all the weights will be divided by this factor, and therefore the inverse of the weight is multiplied by this factor for all the previous weights for the existing point. And then we compute the new weight for the new point we add on, actually here the inverse of the weight, by doing this product. And we go through all the points until we reach the last one. Then at the end of this for loop, inside the W in J and J, we would have exactly the reciprocal of all the weights. Then we go through one final for loop to compute the inverse of that and put it back into the function W, and now would contain all the weights. So what is really nice of this barycentric form is that you can further manipulate it, and that will lead to an even more elegant formula. Let's first apply the formula to interpolate the constant function, which is 1. That is, in the formula, we will put yi equals 1 everywhere. Then we have the following equation. 1 equals just the sum of all the cardinal functions multiplied by 1. And use that form of the cardinal function, we can take out, again, this L outside the summation because it's a common factor. And then we'll be summing over the weights divided by x minus xj for all the j's. And now this actually gives us an expression for this function L here. You see, I can move the summation to the other side of the equation, or take the reciprocal or inverse of it. I'll have L of x exactly equal this summation sign, which is here, to the negative 1. And that is L of x. Then, if we plug this expression for L of x into the formula 2, which is the barycentric form for the polynomial, we obtain a new form, which is like that. So we see that the interpolating data here, w, occurs only in the numerator, and in the denominator you just sum over all these wj over x minus xj. Now this expression resembles the calculation of computing the barycenter of a distribution of mass. And this is also called the second and true form of the barycentric formula. And from the expression, we see clearly why the barycentric formula name was assigned to this formula. Okay, that's all for this video. Thanks for watching.